All right, so what I did was I posted a few video clips for you guys involving angular momentum. Let's first introduce the concept of what angular momentum is, and then after that, we'll show you maybe one or two applications of angular momentum based on those video clips that I've showed you. So if you think about linear momentum, it was P equals mv. Symbol for momentum was P, mass times velocity. Our angular momentum is going to be the rotational analogs of that. The symbol for angular momentum is capital L. And a rotational analog for mass is I, a rotational analog for velocity is omega. So L is equal to I omega. That's how we calculate angular momentum. And essentially, what we want to end up looking at is the idea of something spinning. If something is continually spinning, like you saw the bike wheel in my demo, there's nothing really going to stop it if it's in a frictionless environment. So it'll just keep going, going, going. It has a lot of momentum. Only its momentum is all restricted to rotational motion as opposed to translational motion. All right, now, one of the things that we really focused on was the impulse momentum theorem back in linear momentum. So basically, we've said that average force times time, which was impulse, that would equal your change in momentum, which would be, in this case, delta P. Right? So that would be one way to write the impulse momentum theorem. There's a similar theorem for angular momentum. You can have something called angular impulse. Basically, our analog to force is torque. If you have torque, we'll just write a tau for that, times time. This would be angular impulse right here. So impulse has an angular analog as well. And what that would be equal to is the change in angular momentum. So we're not really going to be doing a lot of math here, but what we want to do is talk about, one of the classic angular momentum problems when we first introduce it. And that's the idea of a figure skater. If you ever watch figure skating, what you see is that the figure skater, when she has her arms out, she's spinning around. And then as she brings her arms in, she starts spinning faster and faster and faster. So what ends up happening is that you've got two cases here. Here's your figure skater. They're twirling around in a circle. We'll make it counterclockwise. And then a good, I would say, estimate for a figure skater for moment of inertia might be about, I'm going to guess, maybe 4. It'd be something reasonable. Kilograms times meters squared. And a lot of people look at that number and they don't understand why. I kind of assume the person would be a cylinder. And that's, that would be a reasonable value for, let's say, maybe a 75 to 100 kilogram person. And then what they do is they bring their arms in. So they might bring their legs in too. So they end up kind of reducing their own moment of inertia because now everything is closer to the center as opposed to spread out right here. So you're going to notice that they can speed up by doing that, and so omega 1 and omega 2 will not be the same thing. What's going to end up happening is omega 2 is greater than omega 1, because what ends up happening is that as you change the distribution of mass around you, bringing it closer to the center, that's going to reduce the moment of inertia. So that could easily make the I value something like 2, depending upon how drastic that change is. Now, if we're gonna say that they've got a decent omega, let's call it, maybe 1 rotation per second here, 6.28 radians per second. What's omega 2? This is going to involve the fact that angular momentum can't change. There is a reason angular momentum can't change. When the figure skaters on ice, they are what we would consider an isolated system. There's no external forces acting on them, no friction, nothing. So that means that you have no external force. That would mean no external torque. And this is why we bring up the impulse momentum theorem for rotation. If that quantity is 0, that quantity is 0. Meaning that if there's no external torques acting on our person that's rotating here, their angular momentum has to be conserved. Now what's going to end up happening is that their speed clearly does change, but that's because their moment of inertia changed. So what we're going to say is that their first angular momentum with their arms and legs spread out is equal to their second angular momentum. And let's write it now as I1 omega 1, I2 omega 2. There is no change in angular momentum here. So this would be 4, this would be 6.28, and then this would be 2, and then this would be omega 2. And when we solve for omega 2, we should get a value that is twice as large as the initial speed. So omega 2 ends up equaling 12.56 radians per second. And what's happened here is that this person is now rotating faster, but they still have the same angular momentum. Looking at this, some people think, oh, this is one of those something for nothing deals. But it turns out that this isn't an easy thing to do. In fact, one of the things in figure skating is a triple axel, I think, is the hardest move to land in figure skating. And that actually takes quite a bit of strength. So let's look at the energy of this as well. We learned about rotational kinetic energy. If I look at these numbers here, and I say that the initial kinetic energy is equal to 1/2 I omega squared, with the I value being 4, omega being 6.28, we'll square it. 1/2 times 4 times 6.28 squared. That's going to give us our kinetic energy in joules. We get 78.87 joules. You look at their kinetic energy afterwards, it's still the same formula, but they've got a new moment of inertia and a new angular velocity here. So it's 1/2 times 2 times 12.56 squared. Let's actually make that look like a 6.
Are you done?
What we end up getting is 157.8 joules. And you can see that the kinetic energy has clearly gone up. So it turns out that this isn't something for nothing. You actually need quite a bit of strength in order to do this, and you'll notice that in figure skating they'll actually start to rotate really fast, because what they've ended up doing is they've actually added energy to them. Bringing your arms in this fashion actually takes quite a bit amount of work. So you could actually calculate how much work was being done simply by using an energy expression. There's our initial energy, there's our work, there's our final energy, and you would find that the work would end up being the difference between these two numbers. So every time they bring their arms in, they do positive work on themselves. Every time they let their arms go out, they're doing negative work on themselves. So they can speed up and slow down simply by bringing their arms in and out while they're in this frictionless environment.